All right, welcome back. Good to see you all. Cold Friday afternoon. I'm impressed that you're here. So, a couple announcements. I don't have my announcements page, but I was just going to say an icon had gotten an email today about the final project. The due date of the actual written work isn't changed. There's the optional presentation date on December 14th, which is a Wednesday. I'll have some pizza at some point after the fall break, Thanksgiving holiday. I will have a sign-up sheet if you intend to participate. Don't have to. There's no grade for it. It's more to try to show everybody essentially like a repository of Stan. Like, here's a model. Here's how I did it, to try to learn from each other. That's the big picture. So, any questions or comments about that? Okay. Now again, it's optional, so you will not get a negative grade by not showing up. I need to be very clear about that. All right. So if you don't show up, totally good. Okay. Now, on that sense, please do consider showing up. I'm not going to beg you, but here, I'll just beg you. But no, I will. I want to make it so that we can try to share what we've done, so students can learn from your experiences as well too. I always look at the project as being some of like an extended chance to work one-on-one with you on data that may be more relevant to you than I'm presenting here. And part of that learning experience could also extend to being able to share what you've learned with other students as well too. So thank you. Class size just doubled. This is great. Okay. So any questions? Yeah, Julia.
If I want to be a presenter that day, what is time limitation?
I will let you know as soon as I know how many people sign up. Okay? But probably 10 minutes, let's say 10 minutes, right around that time with that, and depending on how many people sign up, we'll have more or less time for questions. And the way I look at it is, for the presentation, basically what was the model that you wanted to do? Maybe a little bit of background, like one slide on why, what's the model, and then what's your stand code, and then what did you find? Very formulaic to try to do that, but again, it's optional, and then once we figure out who is available and who is able to come, then we'll know how much time. Okay? Thank you for asking. Other questions? All right. You remember last time? Oh, do I see a question? No. Okay. All right. Remember last time? We got to the beginning of the multinomial model. We covered binomial distributions, which nobody really talks about that much. But I wanted to give you that perspective because why? Because every distribution has pretty much a chance that you could use in some data context. So, but multinomial is really much more prevalent. This is a multinomial distribution. We covered it last time. Basically, the idea is there are n trials, and then there are c categories of an outcome, c outcomes, effectively, right? So think of rolling a six-sided die, right? Instead of the binomial being for whether a probability of a number shows up, like that's only one outcome, the six-sided die would be which number showed up. Right? So this will tell you. Y is the number of times a given number on that die would show when you rolled it face up. And then we went into saying, well, when there's only one trial, though, the multinomial distribution gets called a categorical distribution. And that's what we think of when we do modeling for item response data. Each response is the trial, and the outcomes, or the number of categories, C sub I, each item will have a number of categories, capital C here, and that's numbers of categories. What is this? Hello? Oh! Oh, thank you. No need applause.
Yeah. Will you sing us all together?
What?
Yeah. Let's do it.
What's this?
Happy birthday to you. Happy birthday to you. Happy birthday to Jonathan. Happy birthday to you.
Thank you. Thank you. I'm humbled that you would think of me. So I was hoping that nobody would share this with you, but then I realized Lisa did. So, but thank you for the birthday balloon and the card, and there's a cupcake, even better. I truly do appreciate it. And well, I don't know what else to say. Thanks. Oh, open the card. Oh yes, I see some bays. I don't know that I'll be able to read everything right now. Oh, the coolest professor. Hey, just in case, right there, everybody online, you can see that. Oh wait, is that a Flyers?
Sorry.
No, I'm just kidding.
Don't judge me.
I'm just kidding. I wouldn't judge you about anything but your love for Philly sports. Anyway, thank you all. Yeah, I had a birthday. Happens to us all, doesn't it? So I think this is the year I'm finally going to put my life together and expect big things out of me. So no, I don't know about that. I'm just grateful to be here and in front of you, and I'm grateful you're in my class. So thank you. It's a pleasure to work with each of you. And anyway, I don't know. I'm touched. So. And I don't know. Thank you. Yeah, it's just a birthday. For me, it's just a birthday. I've had a few of them, right? You want to hear a birthday anecdote, just since I'm off the topic now, or do you want to get back to multinomial?
I'd love to hear a birthday anecdote.
So my son's like, Dad, what do you want to eat? Because at our house, we get to pick what you want for eating on your birthday. I'm like, what do you want to eat on your birthday, Dad? I'm like, I don't know, what should I eat? And he says, because I don't usually eat breakfast. I just sort of wait till lunch and whatever. I think you should eat breakfast. You should give yourself breakfast. And so I had breakfast on my birthday. It was amazing. So I had a cinnamon roll. It was great. So, yeah, it's funny to hear it. Then he's like, well, then I think for dinner you should have my favorite food, Steak and Shake. So we didn't. I had some pizza, but it's okay. All right. Anyway, thanks everybody, and thank you for the card and the balloon. That's very nice and very touching. I'm touched. I don't know how to go back to class after this now. So on that note, let's talk about multinomial. Okay. Which is crosses. I don't know what else to say. Take a drink. How's that sound? Okay. Let me ask you, what do you think about multinomial? It seems pretty reasonable. So I'm making a point of trying to emphasize the distributions a little bit more on this, because if you're like me, I don't know that I fully appreciated which distribution was which until I started having to code things. And in Stan, you don't get to have that luxury, right? You have to pick a distribution. So trying to link distributions to the types of models that you may have heard of is sort of what the key in this class is, because then it sort of unlocks the potential for using the same idea. Remember that theory predicting data? That will work with any type of data and any type of model if you can figure out the right distribution to make it work. So I want you to think more broadly than the names and the labels that you see. That's the main thing. Okay? So, oh, wrong one. Right there. So it turns out for each item, there's a set of capital C, what I have in my notes, capital C categories, right? Each one of those categories has a probability, and those probabilities sum up to 1, like any probability would, right? So if in our example data, we have 5 options for each. So we're going to have 5 probabilities, which really means technically we need 4, sometimes called submodels for those probabilities. Right. Turns out those submodels, I mentioned this at the end of the last time, the submodels differ by a few assumptions. Greater response models have this idea that there's an order to the categories, right, proportional odds. Partial credit models is a little bit less ordered. There's an order in terms of pairs of categories sometimes. And then nominal response models is sort of a free-for-all, right? Everything, pretty much as many parameters as possible. Each submodel gets its own set of intercepts or and slopes, or however you want to see those. We're not going to cover partial credit in this class. I'm going to try to get through greater response and nominal response today, but I'll get through it from here's the model and here's how to code it. Here's the model, here's how to code it perspective. Okay? So the greater response model we'll start with. So what do we have here? The probability of a given item response is equal to for a set of categories, It's this sort of difference in, well, here's the core of it right here. A difference in adjacent logit models right here. Right? So the logit for the category below this minus the probability for the logit of the category below it minus the probability of the category for the logit itself. Right? So it's this, and then this P star thing down here, which I usually hate putting stars up, but I know a lot of people do that. This is a regular logit model. This is the probability that y is greater than or equal to a value c. Right? So it's a cumulative logit. So this thing down here is a cumulative logit. Right? So each one, so what's the probability you're 1 or greater? Well, that's always 1 because there's only one or better in arithmetic. Probability of a 2 or better is given by that thing. Right? So if you wanted the probability of a 3 or better and probability of 4 or better, each of those different probabilities show up, and you have to go and subtract adjacent categories' probabilities to get the probability of a specific category. Does that make sense? Right? The order, like this order that you see here, like the first category, it's 1 minus the cumulative logit for that category. That term, that sometimes gets flipped. Sometimes we model increasing categories, sometimes we model decreasing categories. The ramifications are essentially the signs of the parameters themselves. Now, this is where, if I, and I'm told by Professor Aloe that, like, as some people love tidyverse, I love Stan, which is, I keep saying that, but this is where Stan wins for me over JAGS, because to do this in JAGS, which is the program I taught the last time, you have to hard code all the submodels by hand, then you have to hard code the differences by hand. But that's not enough. You have to also create a bunch of starting values because JAGS didn't know what to do when you had multiple categories. So you had not only have to have starting values, that you had to then figure out how to get those across all the chains. With Stan, it's a lot easier. Bless you. The one last thing I want to note is that these intercepts in the submodels themselves are ordered. Right? So that also presented the problem in JAGS. Stan, turns out, there's one line of code. Now, there's one small frustration with that one line of code. But if you're in Lisa's class or you've done things in M+, you'll know the difference between threshold and intercept. Stan will code things as thresholds, but we can always convert them to intercepts by multiplying the threshold by -1. So Stan has a function called ordered logistic. It's awesome, right? It wants y to be an integer, which I'll show in a few slides. But it has 2 arguments in the function. The first argument is the linear predictor except the intercept. So what do I mean by linear predictor? It's like if you're thinking regression model, it's everything that's in the exponent except the intercept or threshold, right? So it handles this intercept as a threshold separately. So in this case, it would just be lambda times theta, right? Then the second argument is a vector of thresholds for the item, right? So what Stan needs to know is how many responses there are and how many categories there are. And it wants the thresholds to be ordered and to be the same size as the number of categories minus 1. But that's kind of it, right? Now, the other thing I'll note, the syntax up above, we have lambda and theta as we had seen them throughout all of our models. But now the prior distribution for the thresholds, I say item intercepts, I should have not copied and pasted. These are thresholds. I put it inside this loop, and that's because, remember how we coded, do you remember how we coded the priors before? We put a vector of means for every one, and then we put a covariance matrix where we just set the diagonal of it to be the prior variance for it. Well, now each item, because in each item for us, we're going to have 4 thresholds. Each item has a vector of size 4 by 1 for the means, and a 4 by 4 matrix for the covariances. So that means each item needs a multivariate normal rather than all of them all at once. Right? That's the one catch. So when we get into the next set of slides, we're going to up the complexity level by 1. Technically what we have here, this threshold actually. Threshold, and each of these is an array, and actually the covariance matrix is a 3-dimensional array. Each of the other two values are 2-dimensional arrays. So we're going to see that in just a moment. Any questions on this? So believe me when I say this ordered logistic makes your life so much simpler than having to code it by hand. Right? You can still vectorize things. It runs fairly quickly. Okay. The parameters, this is where I was mentioning before. Prior to this, we would have one intercept per item, and now we have 4 thresholds per item. So instead of seeing this format where we have a vector of n items for intercepts, now we have an array of n items. And now the type of variable here is ordered. So the other thing Stan does is it allows you to pick an ordered statement to say that this variable, this parameter we have, has an order to it. And it follows the same increasing order that we would expect thresholds to be. Right? Means we're decreasing, -1 is, an intercept is -1 times the threshold. So before we had mu1 was greater than mu2 and so forth, we multiply everything by -1, it changes the direction of the inequality, right? So here ordered does an increasing order across the number of categories or values you give it right here. Yes, I see a question online.
Yeah, so the order of the items refers to like the difficulty that they have?
In this case, it's the parameter for each specific submodel for the item. So in each item, since we have 5 categories, we have 4 what we call submodels, which are cumulative probabilities. So the probability of being a 1 or greater, a 2 or greater, a 3 or greater, a 4 or greater, or a 5 or greater for each of the items. And the ordering reflects the parameters that are the threshold for each of those items. And I'll describe the threshold in just a little bit. But is that a little bit more clear? I don't know if that helps a lot or not.
Yeah, that helps.
Great. Okay, so ordered is a great step forward too, because now you know when Stan samples it, it's going to be in the order you expect it to be for each iteration of the Markov chain, which is very convenient. So again, the bigger difference here is now it's an array, it's ordered, and each category or each item has, in our case, maximum category, which is 5, so 4 thresholds. So it's actually, if you were to think of it as a matrix, it would be a 2-dimensional matrix where it's n items by max category minus 1 columns, right? Yeah.
The object max category, which numbers do we have there?
So that is, I've hard-coded this because all of our items have the same maximum category. I just import that as an integer. In the binomial, I had it as a vector. So if you're in a case where you might have some items where you have 3 categories and some where you have 5, you'll want max category to be different by item to item. But I didn't do that. I got lazy. Actually, I ran out of time with these slides, and I didn't do that here. Does that make sense? Any other questions? Okay. So these threshold parameters are literally, and actually let me go back here. I wanted to go to, actually I don't have it here. Never mind then. No, I want that. Wanted to go to the Stan user's guide real quick, so I didn't put in here what I really wanted to say. So my apologies for not having slides be entirely complete here. But that's not it. Here. If we remember before when I showed you the discrete bounded distributions in Stan where I had that list of all the distributions you could pick, I'm going back to that because I want to talk about the ordered logistic or ordinal regression model here. Wow, that didn't work out. What? Oh, Stan. All right, here is what's happening. Ordered logistic is taking, that's eta, which is our linear predictor except the intercept, right? And then instead of adding to the intercept, so eta in Stan language is our slope times latent variable, lambda times theta. And then you can see where we would just add the intercept to it, it's subtracting the threshold from it. And so by subtracting the threshold, what we just need to do, if we want it to be put back to an intercept, we just need to multiply that thing by -1, right? Because subtracting -1 times the threshold, or -1 times the intercept, leads to the threshold. So I build in my syntax for Stan a generated quantities block where I just convert the threshold over to the intercept. So I'm so much more used to seeing intercept in everything I do. And so I told you, I think earlier in class, oh, you get to control whether you have thresholds. If you use the ordered category, actually you don't. But you can change it to become intercepts. How are we doing with this? This is complicated stuff. Honestly, when I was learning it in class, I think I didn't appreciate, like it's just, I was like, I think I get it. Like to really get it, I feel like for me, I had to code it. I had to actually like know what the variables needed to have in each spot to be able to fill those in a program. Does that make sense? So I say that because I encourage you, try simulating data if you're interested in this. That's a good way of learning how to get these models to work, is if you simulate data from the model equation itself, you'll need all the parameters to make them work. And I think that will help put things into place. It's a good way of trying to understand how to code things and understand it. All right, finally, we need the data block, and this is where another change shows up. We had the question about the max category. I just have it as an integer. But the key thing here, because each item has 4 thresholds now, I have an item by item mean vector. So now the mean vector, so prior to this set of slides, we had just had the intercepts look like this, right? There was mean mu before with a vector. I have to switch that to be an array of n items. That's a vector. So it's an array of vectors, which is actually a matrix. It's 2 dimensions, but this is Stan's weird syntax to make this work. So each item, remember, each item will have 4 thresholds. And what this mean threshold is the prior distribution's mean for each of those threshold parameters. But I have to shift it to an array because now I have 4 parameters per item. So technically, instead of having 1 parameter per item, where I could just have a vector of means, now I have to have a vector of means for each item. That's what this array is doing. Right, so there's 40 parameters in total. And why I choose to do it this way. Now, technically, I could hard code it. You can always do that. But why I'm choosing to do it this way is that in my experience of working with psychometric models, the threshold parameters in the graded response model are the most difficult parameters to make work when it comes to estimation. And this is part of the reason, because we had a comment last time that talked about this. If you have a category that has very few responses that you observed in, the likelihood, the data likelihood for that category is very flat, right? So if you may need to put more informative prior distribution in to go and estimate a nice posterior distribution for a set of threshold parameters. And that tends to happen on an item-to-item basis. So why I structure it this way is that if we run this analysis and we see we don't get convergence on item 1, just for instance, take an item, any item, right? Then when we do, if we want to modify our code, we just have to change our input to the mean vector or the covariance matrix for that specific item to tighten that item's prior distribution. We may not want to tighten all the other, to make all the other ones more informative, but just item by item, we tend to want to change things. Does that make sense? How many of you have had these parameters in other programs not converge before? It happens. It actually happens very commonly, right? It happens a lot. So let's talk a little bit about each item then has a covariance matrix, right? So covariance matrix, the way that we offset that, before we just would say it was a matrix, like this down here, right? So this is one item's covariance matrix, and it's the number of parameters of the thresholds by the number of parameters for thresholds. So each item in our model has 4 thresholds, be a 4 by 4 matrix. But because we have n items and we want to allow that matrix to be different from item to item, we actually have to put an array of matrices together. And this is the part where things start to get a little bit weird coding-wise. My brain doesn't usually work out of more than 2 dimensions. Right? I'm used to a data matrix. I'm used to having rows and columns as a dimension. This is a 3-dimensional array, right? Rows and columns by items. Right? So there'll be 10 items, and then if you just select an item, it's a 2 by 2 matrix. Yeah?
Can you repeat that real quick?
Oh,
Sorry.
I'll try.
You said rows by...
rows by columns by items
By
now.
items,
Yeah, it's
okay.
like a cube of data, if you want to think of it, where any slice will be rows by columns. And so why I say that is, it turns out, this is one nice, it's more complicated than SAM, but multidimensional arrays like this, having 3-dimensional arrays is very handy because there's a data format in R that works with it. It's the array statement, and I'm going to show you that on the next slide. All right? So it is a matter of building a 3-dimensional array of these matrices in R to put into input, but it exists and it's not that clunky. It's just like a little bit more complicated matrix, at least in this example. There are lots of examples of code where I'm like, I have no idea what a 3-dimensional array is doing because I'm trained to think in rows by columns, but this is it. Actually, let me ask, any other questions on the input data? So let me ask you, here's a quiz. Each item has how many discriminations or slopes in this model? 1. And for us, where every item has 5 categories, each item has how many thresholds? 4 thresholds. And then every person has 1 theta. Right, so those are the parameters that we have in our model. Okay, so here's the code for the array for the mean vector and the array for the covariance matrix for the prior distribution of the thresholds. I have to say it slowly because every one of these things is another layer. I'm saying it slowly because I'm going to miss the words, right? So it turns out this mean vector is pretty straightforward. An array of n items where each item has a vector, that's a 2-dimensional array, otherwise known as a matrix, right? I could have just coded it with the term matrix. Because in R, to build that, we just need a matrix. It's 2 dimensions, right? So let me flip over to R here real quick. I wanted to show this. Just a moment. I should have done this ahead of time. Every day, it's a question as to which one I'm going to forget. You need like the Templin bingo card. Forgets his slides, forgets his... Bingo! That would be it. I'd love it, by the way, if you make a bingo of like Templin bingo, that would be fun. Maybe I'll have like a prize. Never mind. Maybe the next time I teach, all right? All right. So what does this look like? So for each mean, we're going to set up a mean of 0 for these thresholds. Remember, they are logits. So centering them on 0 is an easy thing. They won't be that much below or above 0. And then I'm going to make, for each item, a set of 4 zeros for the mean for each of the thresholds. And then this next step right here takes each item's mean and binds them together. So now we have a 10 number of items, 10 rows, by a 4-column matrix. So it's just a matrix. But the covariance matrix is a bit different, right? So here, for any item, this is a covariance matrix of the prior for each threshold, right? I'm having a variance of 1,000, which it's just pretty gutsy, I got to tell you, right? Especially because when we get to nominal response, I'm not going to do this, okay? But now what I need to tell R is to make an array that's 3 dimensions. And to do that, there's an array statement right here. The array, it's like the matrix command in R where you can populate an empty box of data. Here, I'm just letting all the values be 0. You have to tell it the dimensions. In this case, there's 10 items. So each item then has a 4 by 4 matrix. That's what this is saying right here. So when I look at the array, if you loop through, well, heck, let's do this. If you take the first dimension of it, it's a 2 by 2 matrix, right? And if I wanted to say like the first and second dimension, no, it's not showing it the way I want. But anyway, so then I go for each dimension. Right? If I say item equals 1 here, right now what this code right here does is it builds a diagonal matrix where the diagonal is 1,000 for right here. So this is going to populate it. Oops. Like that. So for the very first item, that's our covariance matrix, right? So an item for each, once you condition on the first dimension of this array, it gives you the 2 by 2 matrix of the covariance for that item. But that's what goes into Stan, okay? So if you're wondering exactly what you need to build in Stan, when you look at an array statement, the value that shows up after the word array is the first dimension of what you're giving Stan. And the value, if it shows up after the type, will be the second dimension. There are ways that you can just do them all together, like I had this one right here as array by n item. You could just take all of those and put it on the array statement itself. I didn't do that here. I'm not sure why I didn't do that. Oh, I know why. If you have integers, you can't use a vector or a matrix. Remember, a vector in Stan, what type of data it expects? They're floating point numbers. And a matrix expects floating point numbers. So if you have integer values, which is what Stan needs you to have to do the ordered logistic, then you have to specify it this way. But if you have real numbers, you specify it at least this way. There's another way you could do it. You could actually just put the word real there if you wanted to. But anyway, how are we doing? I think it's that's some charged language in computer science line. Like there's integers, we call them integers. Those are discrete values from negative infinity to positive infinity. And then you have the floating point numbers. We don't call them floating point. We call them real. Which makes you wonder, what are these other types of data? If those are real, are integers fake? Anyway, never mind. Come on, Stan humor on a Friday? Not funny? A Stan dad joke, maybe? I don't know. All right. So how do we call Stan? We call it the same way we did before. We give it the data. Because we still have that problem with our lambdas, we want to keep them positive. So I give it positive values for each. Okay? So a little bit more complicated code. But I still think it's maybe an order of difficulty, maybe like where the other one was, once you get used to it, it's like a 3. This may be like a 4, right? Nominal response is going to be like a 6 or a 7, at least the way I've coded it today. All right, let's take a look at some results. I ran the model. It doesn't take that much longer than the others to run. I have convergence. We would all agree. Looks pretty good, right? And then I have a set of parameters. And what you see here is I have my discrimination parameters, or factor loadings, or slopes first. Now, I output the intercepts, mu. I could have output the threshold, but remember, mu I'm creating in generated quantities, right? If I flip over to R, look at my Stan code, threshold shows up in the model here, but mu is -1 times the threshold, right? So it's just flipping the sign. And since my brain works in intercepts and not thresholds, I just report the intercepts here. It's they're effectively equivalent, right? If you like thresholds and want to keep them that way, go for it. If you like intercepts and want to keep them that way, go for it. If you're somewhere in between, fine, make it work. Whatever. Now let's talk about what we found. What does this mean? So prior to this, in the binomial model, I had an option characteristic curve plot for item 10. This again tells you for any given value of theta what the probability of selecting a given option is, right? So these options now are the 5 categories of the Likert item. Strongly disagree, disagree, neutral, agree, and strongly agree. So how to look at this plot again? If you want to know which option was most likely picked, you look at the line that's at the highest for any given theta. So at theta of 0, the black line, which is option 1, this says a person has a very high probability of picking option 1 for an average theta. And then a little bit above 1, option 2 pops up as the highest. A little bit above 1 1/4, option 3 pops up the highest. At no time is option 4 the highest, most likely to be chosen. And then about 1.5 standard deviations above the mean, option 5 gets picked. And you'll note these option characteristic curves do not look like the binomial ones. Can I just show you what the other ones look like real quick? Huh. There they are. These are very symmetric and sort of rigid, right? And that's because the binomial, to get a probability for each category, it uses its distribution function. Whereas if you look at what we have in the greater response model, that's not it, right here, what's governing the probabilities, in part, are the threshold or mean intercept parameters, right? What we're building here, if we were to really show this, and I didn't plot this, is a series of, there are 4 of those submodel curves that underlie this, those 4 submodels that we have. And because those 4 submodels have different intercepts or different means, their slope changes, right? Their location changes. They're all parallel. They have only one slope, but some may be further apart than others. And some may be right on top of each other, depending on where those ordered thresholds or means are, or intercepts are. And because of that, when we try to express the probability as a probability for category and not a cumulative logit like the submodel would imply, we get a different shape to our probabilities in our option characteristic curves. Does that make sense? Does this fit, for those of you who had IRT, this fits with your greater response knowledge in IRT somewhat? Okay. Questions? No questions. Okay. This is the item characteristic curve. So now what I did was I took these lines and I calculated the probability, took each probability for each line and multiplied it by its value for its option number. And once again, you see the expected value here. So for conditional on theta, this is the average score we think someone would have. The red line is the average score. And again, this is the expected a posteriori, the EAP, posterior mean, to calculate that. All right. Any questions on this? So it's going to look very similar to the binomial. I mean, it's not exactly the same. Now, this is a little bit more interesting. Now we can start to see a little bit differences in models, right? So the big difference between this model and binomial is binomial still treats the data as discrete, but the probability for each category is fixed by the distribution function. There's only one intercept parameter for the whole thing. In this model, it does allow for multimodality of the items because those submodel locations shift. So you can have 2 that are far apart, 2 that are real close together, and another one far apart again. That will give you the multimodality of the probabilities that you're looking for. But if you remember the last time for the binomial, we had a lot higher density here on the lower bound, right? And it's not the same here on the greater response. Here are 2 posterior distributions of theta. These have I'm looking at them right now, and they look about roughly equal in width. I think the blue standard deviation is a little bit higher than the red one, but they're not guaranteed to have the same standard deviation. Any questions on these? Is this boring you? Do you need some explosions? Car crash, train wreck, something like that? No, I don't know. All right, this is interesting though. If you were bored before, this should not bore you. And what am I talking about? Not really a whole lot different, but do you remember this plot from the binomial? It's the EAP estimate of theta by its posterior standard deviation. In binomial, it was very smooth, right? It was very nonlinear, but everything was pretty much in a curve. Here, we have some interesting bounces going around on the bottom. And this is related to, although this is not identical to, the idea of item information in a polytomous item. Information functions in polytomous items are not always single-peaked, right? If you look at an information function for a binary item, it usually has a part of maximum information and somewhere it tails off. In polytomous items, you may have multiple parts of maximum information. Is the way the information function works on the submodels themselves. And so what the ramifications of that is that people sometimes, there's potentially no one maximum part of information in an assessment itself. You may have multiple, right? So what do I mean by that? If we want to think about where our assessment is the most precise for estimating theta, we look at where the smallest posterior standard deviation is, and that's somewhere around a half a standard deviation above the mean. However, it's pretty close about 1 standard deviation of the mean. These two, where these are. But you see there's a little bit of a bump. It goes up higher. People who are at 0.75 have a little bit higher standard deviation than they have at 1 on average. We'll do that. And that's that non-linear information function. We're going to have sort of ridged information on polytomous items. So information functions are really trippy when you start to get away from binary items. By trippy, I mean like some crazy stuff goes on. You dream up a model and you try to calculate information, and you might see weird shapes to it. So, questions? Yeah.
These estimations are based on the items or the categories for each item?
On the categories for each item. So each person's theta, the posterior distribution of theta, is the likelihood of the data, their data, times the prior. The priors are all are normal, but the likelihood of the data comes from this categorical response model itself, right? And that likelihood function is, I'll just show it real quick, is right here. It's the probability for each item. And so because and actually it's really this right here, this probability right here, depending on which response they picked for each item, it's going to be slightly different probability, right? So there we go. All right, this is a plot of theta by the sum score. So if I added all the items together, and again, this is on the original scale of the items. I did not have to subtract 1 from each item like in the binomial. It's also nonlinear, like we would expect, right? This is a logistic model. So we have a nonlinear function between our theta, which is on the model scale, and the sum score, which is on the data scale. Any questions? Yeah?
How many data can we have for each person? So
We have 10 responses per person. Is that what you're saying? Now, how many thetas can we have?
yes.
Up to this point, 1. We can have, so I will talk more about that after break, but just briefly, to identify a model, a multidimensional model, there's a certain set of, you can have a certain set of thetas depending on how many items you have itself. There's a standard that, identification in Bayes is a little complicated. Bayesian people talk about identifying the posterior distribution, whereas pretty much every other class in psychometrics doesn't use Bayes. They talk about identifying the model data likelihood. So it's a different distinction. In the model data likelihood, you can estimate as many thetas as you can put like what we call it row echelon form of the Q matrix. So you have one theta that's measured everything. The second theta measures everything but the first item. The third theta measures everything but the first two. You can do that until you run out of items measuring a theta, or run out of the minimum number of items for theta. So in our case with 8, I think we have 7. I want to say 6 or 7 thetas is maximum. Now it's a bad idea with 10 items. On that minimum standard, you can't have correlations between the thetas, but I'll get to that after we get past Thanksgiving. So I'm also planning on teaching multidimensional models in next fall, and we'll be using Stan most likely for most of it. So we will spend a lot of time talking about setting up minimal identification for that. That's a good question. Other questions? All right. Now let's talk about comparing our logit model here, the ordered logit, the graded response, versus the CFA assumption. Right? We did this with the binomial model before, right? We had the two, and you can see we have they're very related in the middle, but because of the edges, because of the nonlinear result, we have a little bit of a curve to it. Right? It kind of looks like an ogive. That's to be expected. But here's a good plot. Posterior standard deviations. Sorry, again, not, woo, Jonathan, you made a good plot. It's a good plot for information. I like this plot. Ordered logit here. These are our posterior standard deviations. And these are our posterior standard deviations for the CFA or normal model. What stands out to you about this plot? For a lot of our data, so look at the range of y here. 0.24 to 0.30, so that's right about here to right about here. So some of our observations have a slightly lower posterior standard deviation. But as you get further and further away, it's much higher. Right? In fact, this blob of points right here, I believe, is the people who are at the lower bound of theta. So what I'm trying to talk about here is we make a big deal about information in IRT. Like we can build tests with information functions. But that, to me, if you heard the saying, making lemonade out of lemons, if life give you lemons, make lemonades, sort of look on the bright side. Like people saying IRT, we can have an information function. It's like looking on the bright side. Like there's only so much information in binary items. There's only so much information in multi-category items, right? In binary items, it's one bit, literally like the definition, one bit of information per item. So if you think of an assessment as being a collection of these bits of information, for binary items, it's like the least amount of information you could possibly get out of any observation for anyone. For polytomous items, it's slightly more, potentially a lot more. But think about normal. If we truly had continuous items, right, slight fluctuations in that value of the observed response would be meaningful, and therefore stands to reason that those items potentially have a lot more information. So what I'm saying about that is if you look at an information function for even a polytomous IRT model versus a CFA model, the information curves for CFA are usually much higher because it pretends that we have non-discrete, non-integer values. And in that regard, we get bigger, we get smaller standard deviations in our posterior. Not always, there are some that are slightly smaller here. But then we get a chunk that are much larger. So, does that make sense? A little bit? So why I say that is, you don't see people talking about information functions in CFA a whole lot. Now I learned from someone who did, Rod McDonald in his book, but the CFA information, this normal information function is actually flat. And compared to binary IRT models, it's flat and usually much higher than wherever the information function in an IRT model is. So, interesting. So when people talk about this, why do I say that to you? When you think about assessments, what's your way of giving more reliability or more precision for theta? Adding items, right? There's another way though. Think about the type of items you're adding. Because if you only add binary items, each item can only increment information so much. Now, those binary items may not take a long time to answer. If you add polytomous items, like graded responses, you add a little bit more. Now, if you could add truly continuous items to your assessment, there's a lot of potential information in those items. How do you do it, though, is the question. And so this is the basis of why when I talk about, like, when you see in educational measurement, we talk about technology-enhanced items. Have you heard of those before? Like brand new things you can do on a computer, like draw a graph, click multi-select, all sorts of different things. What we tend to do with those, if you think about them, the data we're collecting has a little bit more information to a lot more information compared to binary or graded response type items. However, oftentimes, particularly in the assessment world or industry, we take a response, let's take a multi-select item, click all that are true, right? Click all the things that apply. Well, we often categorize that into a rubric that leads it to be a set of ordinal categories that aren't that many, because it fits in a greater response model. That categorization is cutting down on information that we potentially could use for theta. Now I say it's potential, the item has to fit the data, there's other things that go along. But there's, I think, a whole world of research we could be doing with this in mind. I'm trying to teach you the basis for it, right? With a different type of distribution or a different type of model, we could unlock a little bit more information from those potentially a lot more information from those technology enhanced items. It's just a matter of figuring out what the model is and of implementing it as well too. So just think about that as you look at data. Anytime you have to make a decision about data to recategorize, including correct, incorrect, you potentially lose information from an item because you're going down from you're literally limiting the amount of information it can contain. Right? A 0 or a 1 doesn't have a lot. A 0, 1, or 2 has a little bit more than a 0 or 1. But if you have an item that can range between 0 and 2 in discrete or decimal values, like a slider bar or something, there's potentially a lot of information to it. So, that makes sense? All right. That's why I teach you it this way. Because if anybody's looking for an active area of research, go grab technology-enhanced items and make an item response model for each one of those types. Right? There's a lot of information to be unlocked in there. At least that's my thought. Anyway. Questions? Soapbox. Moment over. Moving on. This is a comparison. This is just taking the normal distribution, subtracting the ordered distribution from it. Here's 0. That's where their standard deviation is roughly the same. And you can see we get a chunk of people who are above 0, so where the normal is bigger, and we get a chunk of people where the ordered has a bigger standard deviation. But generally speaking, well, you can see how that works. Now, if you wanted to compare the greater response model versus the binomial, let's take a look at theta results. Right? They're not identical, but they're pretty close. What's the correlation of this scatter plot? 0.96.
Maybe.
Right? There's a little nonlinearity in parts, and that's because, remember, the binomial has this unimodal assumption for data, whereas the greater response model can be unimodal, but doesn't have to be. And I believe that this little nonlinear, if you follow a line here, the line itself would sort of have a bend in this part right here. I think that's because in the greater response model, you're seeing items that might have had people who might be responding in some of the different modes of items. And that's where it might fit the data better. But to truly determine which model fits better, we're going to have some model fit statistics. But what is this? What am I showing you in these plots? Here's GRM versus binomial. And then here is GRM versus CFA. We now have 3 models applied to the data. Depending on the model you choose, you may or may not give people a score that's comparable. Which one do you choose? I picked the one that fits my theory best. No, that's the wrong answer. Right? Math don't care. We have to figure out how to determine which one fits the data best. I'll show you that hopefully a little bit after Thanksgiving. And again, this is the difference in, or this is a scatter plot of the posterior standard deviations for the ordered logit and the binomial. These look a little bit more related, although not entirely. And this right here shows a difference between the two, right? The binomial tends to be a little bit larger than the ordered for whatever reason. So anyway, any questions? So greater response, I would prefer it to binomial. Like it has more parameters, it probably fits data better. Probably, I haven't gone and defined that yet. Right? I picked binomial to show you, to get us started, because I wanted to give you that broader perspective. Nominal response, let's talk about it. A nominal response model, then, sometimes called the generalized logit model, treats each of these probabilities, or 4 of these probabilities. Actually, no, it comes up with a submodel for each probability specifically. But it usually has to do so with a set of constraints. So literally, what you see here is for each category, we create a logit, right? So category 1 has an intercept and a slope. Category 2 has an intercept and slope all the way down, right? So if you have a person who has theta, if you're building a likelihood function for them, you calculate the intercept plus the loading times theta for each category on the logit side. And then you convert it to probabilities by sometimes called a divide by total approach, where we take E to each one of those sums and we divide it by the sum across all categories of that same exponentiated sum. In STAN, this is called a softmax, right? In IRT, we call this a divide by total approach. Right? So what does this mean? That means instead of working with the greater response model's cumulative logits, we are modeling the probability of each category directly with this function. But we have to make some constraints, right? So for each type of parameter, we either need a sum to 0 constraint, meaning the sum of that parameter across each category is equal to 0, or we need to set one of the category's parameter values to 0. So what do I mean by that? Or what does that mean? So think of it this way for the mean. For our 5 category items, we'll have 5 means. We either need to say that the sum of the 5 means is equal to 0, or, not means, 5 mu's, 5 intercepts is equal to 0, or we need to take one of the intercepts and set them to 0 and estimate 4 of them. Either way, we can only estimate 4 of them. Interestingly, in the STAN user's manual for the STAN documentation, they say, well, now we could really have to specify a prior to identify the posterior on this. This is the distinction between the Bayesian and the frequentist, right? The frequentist, they're only worried about the model data likelihood. The Bayesian has the prior to work with to try to identify the posterior. So I still follow on the model. I want the model data likelihood identified. That's my belief. So this is the constraint you see. Have you learned about nominal response models in other classes? What constraints did you hear about? Did you hear the same sum to 0, or did you hear set 1 to 0? Set 1 to 0?
Yeah, but this is my question. In these cases, those results for each category will be comparing that specific category with a baseline?
Right, right.
Okay.
It's because it's divide by total. Wherever you make the constraint is still included in this total. So what you're going to see is I'm going to, in my code, I'm going to set the very first category. Actually, this is the last category, but I could set I'm going to set the very first category's intercept and slope to 0. But think about what that does, though, because this sum is across every category. By setting that one particular category's values to 0, that means its specific linear particular, the part in pink here, is equal to 0. So e to the 0th power is 1. So I'm always adding a 1 to it. But that's our baselines. Relative to this category is how everything works out, because the divide by total includes that category with the constraint in it. Does that make sense?
Yeah, so those results will be the difference between the specific category and the baseline?
That's right. That's right, in logis. That's right. I don't like to think of it in that way as much because I like to go back to the data scale. Because once we go to the data scale, not in logis, but in data, then we can still draw our option characteristic curves for each, right? So we can plot that. And on the data scale, it's no longer relative, right? Because to get it back to data, we have to apply this inverse link function to get there. So in STAN, this is where the degree of difficulty goes up a bit. I was on the cusp of my standard for STAN. I insist on showing you vectorized code. That's the nerd in me. Why? Because it runs faster. And I couldn't figure it out. I still think you can. I challenge one of you to try to figure it out, or any of you to try to figure it out. I just couldn't figure it out in time to build a lecture for you. And this is not my best lecture, I know that. But, it's better than me being like, sorry guys, no lecture today, I couldn't figure out vectorized, right? First rule of code is make it run correctly. The second rule of code is to make it run correctly quickly, right? So here, let me describe what I'm doing. Turns out Stan has a categorical logit function where it takes the probability associated with each category of an outcome. And it converts that probability, oh no, this is exactly probability. No, pardon me. It takes the logit of each outcome. So in our case, it is expecting this sum for each category, for each person. It then converts this sum to a probability using what Stan calls a softmax function. It's this inverse link function here, the divide by total. Right, e to the thing over the sum of e to the thing. But here, you'll note, in my previous code, I just had item here, and now I have item and observation. And that's because I'm looping across each item and each person to calculate this. That's the non-vectorized version of this code. Now, technically speaking, depending on how your C++ compiler works, it might read the C++ code that Stan writes and find a way to vectorize it also, because it can run a little bit quicker, but that's not guaranteed. So now let's look at what I'm doing inside here. I have, for each category, I'm creating the logit, mu plus lambda times theta, and saving it in this probvect object. Right? So here, I define it in the model statement. It's not tracked, it's not saved in output, but I define this for each person, and then I submit, so I loop across all the categories for a single person, and then I submit that definition to Stan's likelihood for the data. Does that make sense? The other part that's a little different here is because each category now has its own mu and lambda, I have to do the same trick I did with the array before in the greater response model. And so now I have to loop over the mu and lambda to get the prior distributions defined for each. Let's go a step further. The parameters are unordered, so I define them as vectors. But you'll note I'm calling this init mu and init lambda. And I say that I only have 4 of these, right? Max category minus 1. That's because Stan, when you declare a parameter, you can't set one equal to 0. And I'm going to set the very first category's mu and the very first category's lambda to 0. So now I have to define a set of what I'm calling initial values. These are the 4 parameters. And then in a different block, I'm going to set the 5th one equal to 0. Okay? Questions? No questions. So here's the transform parameters block. This is something, I don't think I've taught you transform parameters yet. Have you seen transform parameters in Stan? So in Stan, there's a block called transform parameters. This functions differently than generated quantities. Generated quantities happens before, or happens after you do the sampling, right? Transform parameters happens before. Sort of works with the model block to build things together. And so here, this is where I'm forming the 2 sets of parameters that go into my model, mu and lambda. Both of those are 5 category, 1 parameter for each category, so 5 categories per item. And then I loop over each item. I fix the very first mu to 0. I fix the very first lambda to 0 here. And then I set the remaining terms equal to the values in the init mu and the init lambda. And I have to give these an index here to describe this. What do I mean by that? So let's take item number 1. Mu for that item has 5 columns, right? It's a matrix, right? So mu1, take the first row of the item, there's 5 parameters. I'm saying the second to the 5th, so this right here says 2, 3, 4, 5, is equal to the init mu for that of 1, 2, 3, 4. That's where this other term comes in. This is called an array index. It's the values of the array that you want to assign to the other side. And so because this on this side there's basically expecting 4 values, right? I need this side to give it 4 values. That's how it's working. Any questions? Same thing on the lambda side. So transform parameters is where we start setting constraints. And it turns out, this is why I put multidimensional models and different types of identification after nominal response, because it turns out if you want to use a marker item to do marker item identification on the model data likelihood for these models, you'll need transform parameters as well too, because you'll need to fix one of those parameters to a certain value. So transform parameters is where you set your own constant constraints in Stan for your parameters. It's one way of doing it, at least. Questions? The data, then? No questions? I'll move on to the data. Data looks like...
Jonathan, I actually
go
have a
ahead.
quick question.
Yes.
So, I might have missed it a little bit, but can you give a more general explanation of the transform parameters block and like other uses?
Yeah. One other place for it is, if we don't want to identify theta's scale by setting its mean and variance. So if we don't want to say the mean is 0, the variance is 1. What we often do in a frequentist setting is we fix one of the discrimination or loading parameters to a value of 1, and we free the variance. We estimate the variance, right? So transform parameters is where we would do that. We would set one of the loadings to equal to 1 in that case, and we would then just estimate. We'd have to build the part. So transform parameters is used when we have one or more of our parameters set to constant values. We're basically ignoring the sampling of it. Does that help?
Yeah. So this is basically like just giving a little bit more definition to because the way that I have looked at the data block and the parameters block, data is what we know, parameters is what we don't know, and then transform parameters would be more some more distinct specifications of to help guide the model to do what we want it to do. Is that kind of what?
Partially, yeah. Think of it as also, if we also build a model, sometimes we want, in linear model sense, kind of taking me back to different lectures, but there's something called cubic polynomials where we expect certain contrasts that have certain nonlinear functions to it. You would use transform parameters. So basically, if you say one parameter is a function of the other, I have the mean on this one and I have the mean squared in that one, you would do that here as well too. It's just setting constraints. It's basically parameter constraints that are important to the model is where this shows up. Does that help?
Yeah, thank you.
Thank you. Thank you for the question. Any other questions? All right, data block. The lambda now needs an array. Again, this is just each item now has 4 lambdas and has 4 mu's. All right, so it works the same. We build that array, again with the array syntax in R. Now, here's where things get a little bit crazy. Our initial lambda is the thing we need to set, because remember, initial lambda is where the vector of the 4 lambdas come from. And the way I've defined this model, I've allowed it to be positive for some of them. In the nominal response model, that's not always the case. Depending on which category is either that applies the constraint to it, some lambdas may be positive, some may be negative. So you can't expect them all to be positive. Now, I say this because the very first time I ran this, first of all, I used a mean of 5, and it wouldn't run at all because I blew the likelihood up. The exponent to it just decided to just exceeded the floating point precision. So it wouldn't run. And then I ran it without the initialization function. And I found multimodality with my lambdas. But depending on which type of lambda it was, I had actually set the last category to 0, not the first. And so some lambdas should have been negative, but they look positive, and some lambdas should have been positive and they look negative. I'm like, oh my goodness, this is never going to go. So I decided to pick the first category. The first category, by the way, is where most options were chosen. So when I set it to 0, relative to that, when I allow the other parameters to run, I expect them to be positive. Because if someone picks a higher category, they're more likely to have more of theta. So I fixed the lowest category to 0 for that reason, to allow this to happen. The other part of it is I need to specify this normal distribution to be for each initial lambda. And remember, we have 4 lambdas per item times n items, or 10 items. So we had to specify that too. And if you look at my R syntax, you'll see it. I did the little trick where I just ran a chain 10 iterations without any warm-up to be able to confirm that that had happened. So finally I got it to work. The other thing I will tell you that I needed to do, this is after I copied and pasted code. Get a little bit further down here. So I ended up changing my variances of my hyperparameter, the prior variance, from 1,000 down to 1. And I say this because if you use 1,000, now Stan, where it selects the next proposed value is based on these leapfrog steps using Hamiltonian dynamics. It involves a derivative of the parameter. The deal is, though, it appears that those leapfrog steps take longer when the likelihood or the posterior surface is flat. And so with 1,000 there, it actually took this same analysis with only 1,000 iterations for warm-up and 1,000 iterations for sampling, so 2,000 iterations. It took it 2 hours. When I set it to 1, it took about 5 minutes or less. So this gets really complicated. The nominal response model is very difficult to work with. That doesn't mean you shouldn't work with it. It's actually, there's some beauty in complicated. I've never found something more complicated than I haven't appreciated. I like complication.
Jonathan,
Yeah.
can I ask another quick question?
Yeah.
So what does theta mean in a nominal model?
Theta is a latent trait. It still means.
So it's just like, but since it's unordered, then is it kind of treating each thing almost like as like in a polytomous model where each response has its own probability curve, but
right.
In this case, each category has its own probability curve?
That's right. That's it.
Okay.
And actually, in my first iteration, we know the items are actually somewhat ordered, even though we're fitting a nominal response. We're basically testing whether or not the ordered assumption of graded response applies by fitting this model. It's really what we're doing. But I actually, because we could sum our items up, I actually compared the sum of the items to theta at the end. Now, most nominal models you won't be able to do that, but for these items I can. They're still items. And I found a negative relationship, so I realized my mode had switched, and so I had to change things around for it. But it's a good point. It's difficult to understand what theta means in nominal response because, again, these are nominal categories. You have to figure out, so you have to do an extra step of figuring out, like for each item, what high values of theta are picking, which options they're picking versus which low values are picking. Does that help?
Yes, thank you.
Thank you very much for your question. All right. Here are the results. I'm outputting the estimated mu's and lambdas. You'll see for the very first category, they're all set to 0. I do have good convergence finally. It took me days to figure out to get this to run. I kid you not. So how many of you want to work with the nominal model? No, nobody. No. It's actually really useful. One of our students who is almost done with their PhD is working on nominal response models, and they're very difficult. That doesn't mean you should shy away from them. You will learn a lot about data by working with them. There's just don't do it on a deadline. Like, class, I need slides now. Anyway. Here is an estimate plot of our posterior estimates of theta with our standard deviation. I'm just going to flip these quickly. I know we're out of time. The sum score versus theta. You'll see this is not a linear approach now, and that's because each option is not ordered. And that's what you were saying, Nathan, about that. Here's a comparing of thetas of normal versus graded nominal response. Different posterior distributions. These are all higher. We have more parameters, so there's less information for the theta, basically. The parameters are taking more information of the data to solve. Nominal versus graded response, we get a little interesting divergence there. I think that's pretty cool. And There we go. Last thing, this 1 minute. You can put them both together. You can have mix and match items. I didn't show you that because I knew I was going to run out of time. But basically, remember, the likelihood itself of the data just relies on a distribution function. So where that would be implemented in Stan is in this loop across items. For some items, you might say categorical logit. Other items, you might say ordered logit or Bernoulli logit or normal or whatever. It may just have a different loop across which ones are which. But you can do that. I've run a minute long, and I hate doing that. So let me stop. Thank you for your time today. Don't forget Terry Ackerman speaking at 2 p.m. and 1:10 for those of you in person, but it will also be on Zoom or Teams as well. So he's always gives a great talk, so I hope you'll be able to attend. Thank you. Have a good weekend, Thanksgiving break as well. Send me your questions over email. I'll be happy to communicate with you. Take care. Thank you, everybody online.